Okay, so from we just did the moment of inertia about the axis AA prime, which came out to be ml squared by 12, and then the moment of inertia about the axis at the edge, which came out to be ml squared by 3. Let's write what we call the parallel axis theorem. And that says that if we know the moment of inertia about an axis that passes through the center of mass, then we can calculate the moment of inertia about another axis which is parallel to it and anywhere else. Could be even outside, could be even here. So to find the moment of inertia about BB prime, we could have used the parallel axis theorem, which we will use now. This theorem says that the moment of inertia about any axis is the moment of inertia about a parallel axis passing through the center of mass excuse me, plus the mass of the object times d squared, where d is the distance between the two axes. So in this case, d would be from here to here. So if we use that, and the moment of inertia with the center of mass is given by this equation, because this A prime was passing through the center of mass, it's going to be ml squared over 12 plus md squared. So m is the mass and d is the distance between the two axes, which is L by 2 squared. So if we solve that, we can take the m outside, and we have L squared over 12, and we have L squared over 4. And the LCM of 12 and 4 is 12, so we get 1 plus 3, which is 4 over 12, which is 1 by 3. So this simply becomes ml squared by 3, which is what we had earlier. So we can use this theorem. If we know the moment of inertia about the center of mass, we can find it about any other axis. In this case, it was easy enough to find it here, but there are cases where it's extremely hard to find it about an off-center axis, and then we use the parallel axis theorem. So let's take an example of that kind, and we'll take the case of a cylinder. So if you have a cylinder, let's not make it very long. Okay, here's a cylinder, and here's the axis of the cylinder, and it's going to be spinning about this axis, which we can call AA prime. And we want to find the moment of inertia of this cylinder. So if we take a, let's look at it from above. If we take a ring at a radius r, let's call this capital R, and we take any other r, and we take a thin shell of thickness delta r, so the radius is r and thickness is delta r. That shell is here, and then the shell goes all the way down to the lower end, where we have, so it's like a thin cylindrical shell. Then the moment of inertia, that's for is going to be the integral of r squared dm, and the integration is going to be from this shell goes from 0 to capital R. So the problem is how to write dm, and we'll write the dm as a density times the volume. So the density of this cylinder is constant, so we just take it as rho. The volume of this shell is going to be 2 pi r dr L, where L is the length of the cylinder. 2 pi r is the circumference times the depth become the area, and the area times the length become the volume. So this is the area, the circumference, the area, and the volume. Okay, so let's remove this. We'll use this as dm and plug it in here. So the moment of inertia becomes the integral of r square rho 2 pi r drl. Now L is constant for the whole cylinder, so as we integrate this and change the radius little r from 0 to capital R, so L can be taken out, the 2 pi can be taken out, the rho can be taken out, 2 pi rho L, and we are left with r squared and r cubed dr, 0 to r, and we do the integration is 2 pi rho L r 4 over 4 from 0 to r. When you plug in the 0, we get 0, so this becomes 2 pi rho L capital R 4 over 4. So well, we can cancel one of the 2's, so it becomes pi rho L R 4 over 2. Now we can pick up some things. So if you want to find the mass of the whole cylinder, it's going to be rho v of the whole cylinder. It's going to be pi r square L. That's the volume of the cylinder. So we pick up the rho and the pi and r square. So we pick up an r square from here. We are left with another r square, and we got that, and the L. So we take the L from here and divide by 2. So pi r square L is the volume times rho, so this whole thing is the mass, becomes m r square by 2. So that becomes the moment of inertia about the axis passing through the center, about this axis. Now if you want to find the moment of inertia about an axis that passes through here, all we need to do is ICM, which is this, plus md square. So it's going to be mr square over 2 plus m, and the d is from here to here, which is r square. So that's 3 by 2 mr square. So it's pretty easy to find the moment of inertia. Okay, so we stop here.